Today we're going to talk about more triangle properties, and we're going to lead into kinds of quadrilaterals that we will be working with. So last time we learned a lot of stuff about triangles. We learned ways to prove triangles congruent. We learned altitudes, medians, special lines we can draw in triangles. We learned some new geometry terms. We learned about the Pythagorean theorem. So, when we learned about our ways to prove triangles congruent, we were always given the information and had to draw our own picture. So we're going to focus first on today, what if we're given a picture already, how do we prove two triangles congruent? So we don't have to draw our own, but we still have to say if they're congruent and why, and make our congruence statement. So the three ways to prove triangles congruent again. Or SSS, side, 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 SAS, for side, angle, side, and ASA. Okay, so this one is actually, I think, easier than the first way we looked at triangle congruence, because the picture is already going to be drawn for us. So let's say we have these two triangles. And we need names to call them, so I'm going to say ABC. DEF. So they've already given us the picture, and we still have to say if the triangles are congruent and why they are congruent. So looking at our two triangles, we notice that they've given us information about two sides that match. Side BC matches side DE, and side AB matches side EF. And then they gave us information about this right angle. So we have three pieces of information that already match. We have a side, an angle in between, and another side. So just looking at the picture, we can say, oh, these are congruent by side, angle, side. Well, we need to say the two triangles are congruent to each other. We still need to make our triangle statement. So we need to say our first triangle. Again, I can pick any order I want on my first triangle. ABC. That one's easy enough. But then when I need to make my second triangle congruence statement, I have to go in the same order. So I started at A. A was near the two lines, so we need to look for F. It was near the two lines, and it was not the right angle, so we have to start at F. And then I said B came next. B was the right angle itself, so the right angle on the second triangle is E. And then the only letter left to match up is D. So triangle ABC is congruent to triangle FED. So something else we started to talk about with triangles is how much the angles in a triangle add up to be. So when we have any triangle, we know that the three angles inside a triangle all add up to be 180 degrees. We proved that by ripping off the corners of our triangles and laying them on a straight line, and we know a straight line is 180 degrees. So we know those three angles, angle A, angle B, and angle C in a triangle always add up to 180. And they don't have to be labeled ABC, they can be labeled anything. But we do know that they add up to 180. So we can also consider what's going to happen if I maybe have a line extended on my triangle. We call this angle outside, let's see, remote interior. We call the ones inside remote interior angles because they're far away, and we call this an exterior angle. So exterior, and this is remote interior. So again, let's give these angles names so we can talk about them. This time I'm going to label them inside with XYZ. We'll call the exterior angle W. So we already know X plus Y plus Z is 180. We know that the three angles in the triangle add up to be 180 degrees. But we could also look at Z and W on their own. Here's angle Z, here's angle W, and we say, well, hey, those two angles are on a straight line. I also know Z plus W is 180 degrees. Well, we have some things that are in common. They both have Z's, and they both have equal to 180. That means all the other stuff should also be equal to each other. X plus Y should equal this W because they're almost the exact same equation with just one letter instead of two. So that means those two remote interior angles equal that outside exterior angle. And we're going to use that property to solve for X in some triangles, similar to the way we solved for X when we just had complementary or supplementary. Remember, complementary angles added to 90, supplementary angles added to 180. So let's say we have a setup like this. Gotta give everything on our triangle a name. Let's do A, B, C, D. And they give us some information. Let's say we know this is 2x plus 10 degrees. And we know that this is 2x. I'm running out of room, so it's going to end up bleeding outside the triangle, even though it should all be inside. Minus 8 degrees. And let's say we know the angle, sorry, I put squared instead of degrees. Let's say we know the angle outside is 92 degrees. Well, since we know that these two interior angles should equal this exterior angle, we can set up an equation. Just like when we knew two angles should add up to 90, we could say the first angle plus the second angle equals 90. So we're going to set up our equation. We know that 2x plus 10 plus 2x minus 8, those two angles added together. 2x plus 10 was kind of like angle x, 2x minus 8 was kind of like angle y, equals that outside angle, 92. Once we have an equation that's simple enough for us to solve, I'm going to combine my like terms again. 2x plus 2x is 4x. 10 minus 8 is positive 2. That was our second set of like terms. Equals 92. And now we have to do our opposite operations. Opposite of adding 2 is subtracting 2. So we'd end up with 4x equal to 90. Opposite of multiplying by 4 is dividing by 4. So x would equal, 90 divided by 4 is 22.5. Again, I don't say degrees because that was just us finding x. If I wanted to go actually find the degree measure, I would have to plug that back into my equations. So if I, say, wanted to find the measure of angle A, we know the equation for angle A is 2x plus 10. So everywhere I see x, I'm going to replace it with 22.5. 2 times 22.5 is 45, plus 10 is 55 degrees this time, since I found specifically angle A and I wasn't just looking for x. So the last thing we're going to talk about is types of quadrilaterals. So we know with our triangles, we've covered quite a bit of information. We know how to prove them congruent. We know more information about the angles inside a triangle. But we also want to talk about quadrilaterals and what kind of quadrilaterals exist, and how much the angles in a quadrilateral add up to be. So let's say I have a triangle. We know the angles inside a triangle add up to be 180 degrees. Let's say I take this triangle, I'm going to copy it, actually I'm going to clone it, it's easier, and I rotate it, and I put the two triangles together. Now assuming my lines were completely straight instead of a little bit curved, maybe it would be better for us to do this with one of the smartboard triangles, so that it comes out a little bit nicer. So if I just didn't mean to change the size of that. If I rotate this triangle and line them up exactly, we see that we end up with a quadrilateral, a four-sided figure. So when we're talking about a quadrilateral, it has four sides. And this one kind of looks like a square. We don't know for sure without more information about it. But just because it's a square doesn't mean all quadrilateral sides have to be the same. Quadrilateral covers any four-sided shape whatsoever. So there's four sides, and we know the angles in a triangle add up to be 180. So those three added up to be 180. And if we look at the second triangle, those three added up to be 180. So in total, we know a quadrilateral adds up to be 360 degrees. So four sides and the angles add to 360 degrees. Well, there's actually quite a few different types of quadrilaterals. The first one is called a trapezoid. The key part of a trapezoid, again, all of these will have four sides. That's a given because they're quadrilaterals. Quad meaning four. But a trapezoid, one of its main properties is that its top side and its bottom side are parallel. And this could be rotated so it was left and right, but we usually call this base 1 and base 2. And then the reason I drew those arrows on there are because that means parallel. Just like when we put lines on a figure, it means those two sides are the same. So a trapezoid has two parallel bases. Now it doesn't matter what's going on with the other sides. We don't know if all four sides are the same or not. We don't know exactly what the angles are. This one looks like it has maybe some matching angles, but that doesn't have to happen. I could have a trapezoid more like this. This is also a trapezoid, again, if my line was completely straight. These lines are still parallel, even though we now have some 90-degree angles involved. So that's our first quadrilateral. Our second quadrilateral is a kite. And it's exactly like it sounds. It's like the old school kites you imagine. The kite looks kind of like an elongated diamond almost. And it has two sides the same and two different sides the same. So on this one we have the top two sides are the same, that's given by the 1 mark, and the bottom two sides are the same, is given by 2 marks. Next we have a parallelogram. Parallelogram, again, has 4 sides. All of them do. All of these quadrilaterals have 4 sides. But now, each set of sides are parallel. The top and bottom sides are parallel, and the left and right sides are parallel. It's kind of similar to a trapezoid in that it has some parallel lines, but now both sets of sides across from each other are parallel. Again, it doesn't matter if all 4 sides match in length. A parallelogram is kind of like a tilted rectangle, and a rectangle doesn't have to have all 4 sides the same. We also have a rhombus. Which is kind of like a tilted square. So this time all 4 sides must be the same, and the top sides are parallel to the bottom side, and the left side is parallel to the right side. So a rhombus is like a tilted square, where a parallelogram is like a tilted rectangle. But a rhombus still fits the definition of a parallelogram. A rhombus has 2 sides parallel top to bottom, 2 sides parallel left to right. So a rhombus is also a parallelogram. It can have more than one name. Sometimes they fit within more than one category. And the last 2 quadrilaterals are easily recognizable. We have a rectangle and a square. So a rectangle, the 2 sides across have to be the same length. 2 sides, top and bottom, have to be the same length. And now we have to have 90-degree angles in every corner. So just like a rhombus can be called a parallelogram, a rectangle can also be called a parallelogram. A parallelogram just had to have the top sides parallel, left and right side parallel, and that's also true for a rectangle. The left and right side are parallel to each other, top and bottom sides are parallel to each other. So a rectangle can also be called a parallelogram. And our last one is a square. A square has all 4 sides exactly the same, and it has right angles in all the corners. And if you add 4 right angles together, we do get 360, so we know a quadrilateral does add up to be 360. And its sides still have to be parallel to the sides across. So the top has to be parallel to the bottom, left has to be parallel to the right. And again, square could also be called parallelogram, or a square could be called a rectangle, or a square could be called a rhombus. It fits into a lot of categories. There's nothing saying that our rectangle can't have all 4 sides matching, so we consider a square also a rectangle. There's nothing saying the rhombus can't have 4 right angles, so we consider a square also a rhombus. And same thing, we consider a square also a parallelogram. So don't forget, we have an assembly tomorrow in class, and I will see you guys tomorrow.